So this is lecture 20 of Philosophy 201 Introductory Logic, and probably the last lecture of this semester. So today we're going to cover a really important skill, and actually it's a skill that if you don't learn, things are you're going to have a difficulty putting everything together. The thing is, to this point, you probably have pretty good intuitions about how to prove stuff, but you're missing a key element. It's really impossible to become a master of proving things if you don't also have a grip on what cannot be proven. Now, there is actually a big challenge about that with predicate logic. So with propositional logic, we developed the truth table method. And the truth table method is an extremely reliable method for checking if something can't be proven or not. I don't say it's efficient, because if you have a long argument that has many atomic sentences in it, the truth table method becomes exponentially more time consuming. So that's the problem with the truth table method. Now, predicate logic, we don't yet have anything that resembles that. We don't have any means of checking that something can't be proven. So that's what the focus is today, is how do we check that something can't be proven in predicate logic? The bad news is there's no algorithm for predicate logic. That's actually something. It's not just that people haven't tried hard enough to find an algorithm. We now have proofs that there cannot be an algorithm that would check whether a predicate logic sequence can be proven or not. But that's a subject for an advanced logic course, when you'd study what can or cannot be done. However, the good news is, when you can find a solution to the question whether or not a predicate logic sequence can be proven, it's a more creative exercise. So you have to actually engage in a method of discovery to try to discover an argument that a predicate logic sequence cannot be proven. And so today I'm going to show you how to do that. And again, this is really verging on where science verges over into art, because can't be precisely a science. There's a little more art, the art of finding counterexamples. So that's what we're going to talk about today. Okay, so remember the single turnstile, phi turnstile psi, means there is a correctly written proof using our proof rules that starts with premise phi and ends with conclusion psi. Now, if our proof rules are good, that is, if they capture the intuitive notion of valid argument, then it should mean, if there's a proof from phi to psi, that in any situation in which phi is true, then psi is also true, because our proof rules should be safe. That is, they should preserve truth. Okay, so let's look, for example, at the example below here. So do you think that there's a proof that starts with the sentence FC and ends with the conclusion for all x fx? Now, obviously, if you know how to use the proof rules, if you tried to prove that, you would get frustrated. It would not work. For example, if you tried to do universal introduction on FC, you can't, because it would violate the restriction on universal introduction. But at this stage, until we go through the material today, there's no way you can argue convincingly that it can't be done unless you have a new technique. But let's start in the first part of this lecture. What we're going to do is we're going to start with the intuitions behind the technique. So the intuition is, can we think up a situation where the premise is true and the conclusion is false? Okay, in a moment, in a few minutes here, we'll make it more precise what it means to think up a situation. But let's start with the intuitive idea. Let's just think of a situation where that premise is true and the conclusion is false. So what do we mean by think of a situation? Well, the symbols here, the symbol F, the capital letter F, it's a predicate symbol, but right now it's uninterpreted. It has no meaning. So to think of a situation is to give the symbols meaning. So the question is, can we give the symbols, capital F, lowercase c, meaning such that the premise is true and the conclusion is false? There comes the creativity, because we just have to imagine situations. And the truth is, there's infinitely many situations. So you can't just process through all situations before lunch on a given weekday. You have to somehow, how do you search through an infinite collection? Well, that's where creativity comes in, is somehow you manage to find in the infinite collection the one thing that you want. Now, this is going to be an easy one. I'll just come up with a trivial example. What if the name C named the person Billie Eilish? And what if the predicate symbol FX was the property, picked out the property having green hair? Then the premise would say Billie Eilish has green hair, which I think is true. Maybe it was true in the past. Let's suppose we're talking about the past. The conclusion then would say everything, or if we restrict our quantifiers to people, every person has green hair, which is false. So there's a situation where the premise is true and the conclusion is false. Okay, that's a counterexample. So I'll write that down very clearly now. It's not yet a precise counterexample because we're going to need to, the standards for producing a counterexample are going to have to be a little more tight, because what we don't want is we don't want there to be the possibility of disagreement about whether something really is a counterexample or not. Okay, so because, for example, you might meet somebody who says, I don't know whether Billie Eilish has green hair, or I don't know whether to believe what you're telling me. So then there's dispute again. You want this to be undisputable that you have a counterexample. So the goal in the second bit of this lecture will be to say, here's a very precise way you can present to somebody a counterexample, and there'll be no dispute that it is a counterexample. It's a case where the premise is true and the conclusion is false. Okay, so let's talk about one more example from an intuitive level. Do you think that we could prove from the premise for all x in parentheses fx or gx the conclusion for all x fx or for all x gx? Okay, should that be provable? If you tried to prove it, I promise you, now I don't want you to have to go through waste your time on futile exercises, but you could pause this lecture now and try to prove that and see how you run into trouble. I promise you will run into trouble if you try to prove that, because it is not provable. So let's try to think imaginatively of a case where that premise would be true and the conclusion would be false. So here's an exercise I do want you to carry out, or I think would be good for you to carry out, is pause the lecture, ask yourself, can you think of a domain of things? It can be real, it can be imaginary, as long as it's a coherent imagination. A domain of things where it's true that everything is either, and then find a meaning for F and a meaning for G. They can be anything you want, but find an example where everything in the domain is either F or G, but it's not true that either everything in the domain is F or everything in the domain is G. So I encourage you to pause for a moment and try to think up your own example. The example I will give here is, how about take the numbers, the whole numbers, so take 1, 2, 3, all the way up to infinity. That's going to be my collection, my domain. And then I'm going to assign the meaning. I told you can choose whatever you want for the meaning of F and G. They're uninterpreted. That's your creative choice how to interpret them. I'll interpret F as is even, and I'll interpret G as is odd. So I'll take a domain, is going to be the whole numbers. So that's 1, 2, 3, and so on. The meaning I'll give to F is, I'll let that be is even. The meaning I'll give to G is odd. And then we just check, is the premise true? Is it true that every number is either even or odd? Now, not all of you are mathematicians, but yes, that's something we assume about the numbers here, right? Is they're all even or odd? So that's true, the premise. Every number is either even or odd. Is the conclusion true? The conclusion is a disjunction. For that disjunction to be true, one of the two disjuncts would need to be true. But the first disjunct says every number is even. That's false. The second disjunct says every number is odd. That's also false. So the disjunction as false. So that makes the premise true. This example makes the premise true and the conclusion false. So it's a counterexample. Okay, I do promise you that if there is a counterexample, a real bona fide counterexample, then the sequent cannot be proven. Okay, that may seem like magic. And if you're a very critical thinker, it should be one thing that leaves you a little uncomfortable, because I haven't given you a proof that if there's a counterexample, then there is no proof. I promise you there is a proof. In an advanced logic course, you would learn to prove that. Actually, there's an example of it later in the textbook for this course, but we're not going to get there this semester. So let's move on. And now one more slightly more sophisticated example, and then we're going to start to tighten things up a little bit in terms of how to present a counterexample in a convincing way. Okay, so here's an example of an argument that uses multiple quantifiers and a relation symbol, not just a predicate symbol. So I'll read this back to you in Loglish, so English mixed with logic. The premise says, for every x, there is a y such that x bears the relationship to y. So for anything, there is something else such that the first bears the relation to the second. Okay, the conclusion says there is a thing such that everything bears the relation to it. Okay, there is a thing that everything bears relation to. So the first says each one thing that paired to something. The second says there's one thing that everything is paired to. So intuitively, the second is stronger than the first. Okay, so let's try to think now of an intuitive counterexample where the premise is true and the conclusion is false. Okay, how about the following? Let's take the domain to be people, so living human beings or human beings who have lived in history, human beings. Okay, and let's let the relation, again, as we did with the predicate symbols F and G, we get creatively to choose a meaning. So R is a bare symbol that could represent any relation we want to. So any relation that holds between human beings, I'm going to choose a relation where Y is the mother, the biological mother of X. Okay, so I'll choose RXY to mean Y is the biological mother of X. Okay, so then under those conditions, under that interpretation, the premise says for every human being X, there is a human being Y such that Y is the biological mother of X. That is true if you're looking at, for example, so as long as you think each human being has had a biological mother, okay, we're not going to get into metaphysics. Maybe that's disputable. That's one reason, again, why in a moment we're going to go to make our counterexamples more uncontroversial, okay, less controversial. But for now, just say intuitively among the living human beings, or maybe even if you're like, suppose you have some strange theories, you might even just say, well, there's a group of human beings such that everyone has a biological mother. But the conclusion says there is one person who is the biological mother of all people. That's false, right? That's definitely not true. It's a much stronger claim, and it's not true. So the premise is true, the conclusion is false. That's a counterexample. Okay, so I promise you, again, that means that the conclusion can't be proven from the premise. Our proof rules have been fine-tuned so that if there's a counterexample, then you can't prove the corresponding sequent. Okay, so now on to the next bit. So that's the intuition of how to show that something can't be proven is you produce a counterexample. A counterexample includes a domain and an interpretation of the symbols, in particular the predicate symbols, the relation symbols, if they're names of the names. Okay, but now let's tighten it up. What do we mean precisely by a situation? For this, we're going to need a little bit of what's called the theory of sets. The theory of sets is a big thing, and mathematicians study it. We just need to understand it on an intuitive level. Okay, so the basic idea in the theory of sets is there are things called sets. They're collections. You don't need to know anything about what's in the collection at all. The only question is how many things are in the collection. And we're allowed freely, for the purposes of this course, to assume that for any size of things you can think, there is a collection of things of that size. So there are finite sets. There's actually an empty set, a set that has no members. There's a set with one element. There are sets with two elements. There are sets with n elements for any finite n. There are also sets with infinitely many elements, like the natural or whole numbers that has infinitely many elements. So we have arbitrarily large collections of things called sets. The basic relationship we begin with, we take as primitive in understanding sets, is the notion that something is an element or a member of a set. And that's represented by this symbol, which you probably have seen before. So this symbol here, the little epsilon, and then it says A, little epsilon S means the thing A is a member or element of the set S. So it's like a bag, the set, and it's like there's pebbles inside the bag, and the pebble's an element of the bag, the member of the collection that's held in the bag. Okay, one other notion that will just be helpful for us to introduce is the notion of subset. That's different because an element is a thing in a set. A subset of a set is another set that happens, whose elements happen all to be contained in the larger set. So it's a sub-collection of the original collection. That notion of being a subset is definable in terms of the notion of being a member in the following sense. We say that A is a subset of B. That means every member of A is a member of B. So actually, the truth is we can write that out as a predicate logic sentence. It means this: A is a subset of B means for anything that is an element of A, if it's an element of A, then it's an element of B. Okay, that's what it means for A to be a subset of B. Okay, if you are curious to know more about set theory or feel like you'd like to be more precise, you can look in the textbook on pages 144 to 155. That's not assigned reading, and I believe that you'll be able to solve the current problem set without reading that. However, if you'd like to sharpen your knowledge of the axioms of set theory, what is a permitted construction, what the definition of the various notions are, you may look on those pages, 144 to 155. Okay, so let's assume we understand the vague notion of a set, of members of a set, of subsets. And with those notions in place, you can, of course, talk about things like the overlap between two subsets, the intersection, the union of two subsets, the complement for the things outside of a subset, and so on. So we'll just use those notions freely in now making totally precise the notion of a situation. Okay, so what is a situation? This is like, so real life situations, like look around you, look behind me. They have lots of structure, right? So there's objects, they have relations between them, they have properties. But the idea behind a set theoretic situation is we strip away a lot of the superficial features and we just sort of take the bare bones structure of how many things there are, and then we add back in a few relations between the two. So that's how we're going to describe a situation now. So given some predicate symbols, relation symbols, possibly names, a situation is going to require us to give two things, although the second, we'll see, the second thing is put together here as 2 and 3. The first thing in a situation is you need to give a domain. So that is going to be what is out there. Now, this is, to be able to describe a situation like this is really, it's like having godlike power, because you don't have to assume a situation as you describe it is real. It doesn't have to exist in our world. You are creating an imaginary world, and the only constraint on your imagination here is the rules of set theory. So again, your world can have, now the truth is we require for logic, you can't create an empty world. If you want to get philosophical about that, you have to take an advanced logic course. For this course, when you create a situation, your situation has to have at least one existing thing. It can have more than that, as many as you want, but it has to have at least one. That's your domain or your universe. So when you specify a situation, or sometimes called an interpretation, that's interpreting the symbols, then what you need is a domain, call it M, call it any other letter you want, but the situation has to be a set of things, or the domain has to be a set of things. Okay, and the next thing you need to do is then each of the symbols that you're trying to interpret need to get a meaning in that domain. So for example, for names, each name has to name a thing in the domain. Again, you freely get to pick, no constraints. In fact, if you have 25 names, they can all name the same thing if you want. They can't be empty. That is, they do have to name something, but there's no restrictions on what they name. They all have to name something in the domain. Okay, so each name must be assigned to an element of the domain, and each predicate symbol must be assigned to a subset, a collection of things in the domain. So to give you the intuition of that, so suppose I said my domain is the books on the shelf behind me, and suppose I said I have a name, say the letter C, and C is going to name, and I pick out a certain book on the shelf behind me. I go, that name, C is going to name that book. But then also I could take a predicate symbol, say F, and I could say I'm going to interpret F to mean all the books whose cover is red. So that would pick a subset of the set of all books on the shelf behind me, the set of red books. Okay, so that would be a situation. That would be the interpretation of the name C and the predicate symbol F, if F was the one I was interpreting as, is red. Okay, that's how you precisely specify a situation. I'll come back momentarily in just a little bit to how do you interpret relation symbols. So a symbol like R, X, Y, that's going to be a little more complicated. We'll come back to that. Let's just now produce some more precise counterexamples. Okay, so what you need also now is to be able to compute very precisely, given an interpretation of the basic symbols like the predicate symbol F, we now want to be able to say whether sentences are true or false under that interpretation of the symbols. To do so, we actually have to build up. So in other words, what we'll do is we'll start by assigning meaning to the most basic parts of our formulas, and then we'll assign meaning growing outwards to the whole formula so that at the end, a sentence turns out either to be true or false. Okay, so here's how we do that. So for those of you who have practiced doing computer science, this will be a familiar technique, because what we're doing is what's called a recursive definition. So we're recursively defining the interpretation of formulas based on the interpretation of the basic symbols in them. We did the same thing with truth tables. That is, remember, we assign the atomic sentences true or false, and then we compute the truth or falsity of more complex sentences in a recursive fashion, right? That is, we say, once we know whether say phi is true or false and theta is true or false, then we can figure out whether their conjunction is true or false, and we just keep building up like that. We'll do the same now with formulas, not sentences, but formulas. So they might have free variables. So it's a little more complicated, but here's the basic idea. Every formula with a free variable x, so something like, let me just give you an example, right? So you say, what's a free variable? Well, it just means a variable that a quantifier hasn't been put on yet. So a formula like fx and gx. So suppose we have an interpretation M. We know the meaning of F, so that is, we know which things are F's. We know the meaning of G, so which things are G's. Then the question is, what things are F and G? Now that should be totally obvious. What the right thing to do is they should be things that are both F and G. So that's exactly what's going to happen next. So in step one, if you already know the meaning, so that is the set of things that are phi, any formula phi, and the set of things that are theta, any formula theta, then the set of things that satisfy, that's a logicians like to use that word. They borrow the word from English, satisfy. So in other words, the things that meet the criteria to be phi and theta, well, they're just the things that are both meet the criteria for being phi and the criteria for being theta. So in other words, in terms of sets, it's the overlap of those two sets. So down in the picture there, the elements that satisfy the formula phi and theta is the overlap of the elements that satisfy phi. So those things in the square or the circle on the left, and those things in the circle on the right. Okay. Similarly, now it should be intuitive how you just keep extending that in different ways. So how do you do that for disjunction? If you have the meaning or the things that are phi and the things that are theta, what are the things that are phi or theta? That's the union of those two subsets. So all the things that are in either one of them. okay? The value of not phi, if you know the value of phi, the value of not phi is the things that are not in the subset that corresponds to phi. So things that are in the complement of the subset for phi. So I'll just draw a quick picture so you see that in front of you. So in other words, if this is the domain M, here are all the things that are in the domain M. And suppose we already have, this is phi M, then not phi M, that is the meaning of not phi, are the things that are not in phi. That's the extension, we would say. Okay, so now we can use this, this way of specifying the interpretation of all the formulas. Now we can use this to be very precise in showing how a premise can be true, but a conclusion false. So to give counterexamples that are precise. Here's an example that captures that a counterexample, a precise version of the very first thing we did in the session, in the lecture today. And that is, how can we show that the premise FC could be true while the conclusion for all x fx is false? I chose an interpretation where my domain here, the big oval, is just a set with two things. Notice again, the two things are just dots. I don't have to say a word about what those two things are, what their other properties are. All that matters is there are two. I chose the name C to denote. Remember, I can choose whatever I want for it to denote of those two things in my domain. I chose it to denote the thing on the left. I also chose the predicate F to apply only to the thing on the left. That makes FC true because the thing named by C is in the extension of the predicate predicate F. So C is an F in this interpretation. I have an interpretation where C is F. Didn't have to do it that way. I could have also interpreted it, but my goal here is to show the premise FC could be true while the conclusion for all x fx is false. I purposely also chose to interpret F so that one thing is not F. So the thing on the right in the picture is not F. So therefore, the conclusion for all x fx is false. Now, this example is not more illuminating than the original silly example. You know, Billie Eilish has green hair, but not everybody has green hair. But it's, of course, totally non-controversial. You just stare at the diagram. The diagram makes it true that C is an F, but not everything is an F. Okay, so that's a counterexample in presented precisely in set theoretic form. Now, I could make this even more precise. This is a picture for those of you who like set theory, think, okay, let's see this very formal. I could do the following kind of thing. I could say my domain here is a set M, and well, let me just make up fake names for the things that are in the set. Let's say they're alpha and beta. So alpha is the thing on the left, beta is the thing on the right. And then what I did is I said the extension of C is alpha. Now notice C names an individual, not a set of things. It names just one thing, whereas the predicate symbol F picks out a sub collection. So 0, 1, or more things within the domain. And I picked the extension of F to be the singleton subset alpha. So alpha, the collection of things that only contains alpha. That's why F is the circle around alpha. C names the one thing that's inside that circle. Okay, so that's a counterexample. Okay, we can also do the same thing for the second example we gave at the beginning of the lecture, and that is, how can we show that for all x in parentheses fx or gx could be true while the conclusion for all x fx or for all x gx is false? Okay, the example I gave originally was numbers. I said take the whole numbers, let f be the even numbers, let g be the odd numbers. Of course, for those of you who are not number people, you think, oh, okay, so that's I'm not sure I know what he's talking about. But now this picture, it's a different example. Again, I can choose whatever domain I want. Now I've chosen a domain with just two things. So the two dots in the oval are the two things. I chose the extension of f to be the singleton subset that's just the thing on the left. The extension of g is the singleton subset that's just the thing on the right. So they're disjoint, f and g. Nothing is both f and g. Everything in the domain, there's only two things in the domain. Everything is one of the two, but not everything is f. So for all x, fx is false, right? Because the thing on the right is not an f. For all x, gx is false because the thing on the left is not g. So the disjunction for all x fx or for all x gx is false. The premise is true. Everything is either f or g. It's not true that everything is f or everything is g. Okay, now one slight complication that you'll have to deal with on the problem set is, what if there's a sentence, an atomic sentence like P, that has not been constructed out of predicate symbols and relation symbols and quantifiers? What are the rules of the game under those conditions? Well, the good news is the rule of the game here is that you can assign P whatever truth value you want. It's an atomic sentence. It's an independent variable qua truth assignments. You can assign it true or false, whatever you choose. Again, these are the exercise of creating interpretations is a creative exercise. You try to find an example that gets you what you want. That is true premise, false conclusion. If you can find example, the argument's not valid. So I'll just use that freedom to show you that now very precisely, that the sentence for all x, the conditional, if for all x, fx, then p, can be true, while the conclusion for all x, in parentheses, if fx, then p, is false. Now, if I just spoke English, if you couldn't see the symbols on the page, I would have a hard time telling you the difference between those sentences. Now, I could say, yes, the first is a conditional, the second is universally quantified, but they sound alike, right? The first says, if for all x, fx, then p. The second says, for all x, if fx, then p, under the parentheses. Okay, so it will help you understand what's being said differently in the two cases if you see precisely how the first can be true while the second is false. And here's an example. So look at the oval I created below, a domain of two things. I can freely choose which of those two things are f and which are not. I've chosen it. The only thing that's going to matter is one of the two is f and one is not. So for all x, fx is false. However, there is something that is f. Okay, for all x, fx is false, but there is something that's f. And I'm also going to just choose p to be false. So now let's evaluate the truth value of the premise. The premise says, if for all x, fx, then p. The sentence for all x, fx is false. However, the sentence p is also false by assumption, which makes the whole conditional true. So that sentence is true. Okay, the second is a little more tricky. We have to think about what the second sentence says. It says, everything has the following feature. So that's the way to read these universally quantified sentences. It says all x, for any x, the following is true. So the way to check if that's true in this example is to go plug in, sort of make up names for the individuals in the domain and plug them in one by one and evaluate. Okay, fortunately, we only have two elements in the domain here, so we can just run through a quick evaluation. So let's suppose the guy on the left is named A and the guy on the right is named B. Okay, so then to check the claim for the guy on the left, it says if FA, then P. A, the guy on the left, is not F. So that's false. The guy on P is false. So it's true of A. Fx arrow P is true of A. Okay. However, if you look at FB arrow P, FB is true. P is still false. So that's false. So the universal claim is false because for the universal claim to be true, it would have to be true of every individual in the domain. It is true of the individual on the left of A. It is true that if A is F, then P, because A is not F. That's negative paradox, right? Or in this case, the truth table, when the antecedent of a conditional is false, the conditional is true. However, it's false for the thing on the right. We've called B here. So the universal claim is false. Okay, so for all x in parentheses, if fx, then P is false. Okay, so that's it for examples, interpretations where we have just one variable, where we have just predicate symbols and atomic sentences. The last thing to talk about in this session is how to produce interpretations when you have sentences that have relation symbols. So remember that in predicate logic, you have predicate symbols that have just one place after the symbol, so like fx, but then also we have these n-ary, so more than one possible slot after the symbol. So right now we'll just look at binary relation symbols like rxy. So a binary relation symbol, when you interpret it, becomes a relation that holds between two things. So if you were to do intuitive interpretations of your symbols, you might say something like, I'll take the relation symbol rxy and interpret it to mean x is the mother of y. Or I might take the relation symbol rxy and interpret it as x is taller than y. So you can interpret it as you want. And again, if you can come up with an intuitive counterexample, then most likely a counterexample where the premise is true and the conclusion is false, then most likely it can't be proven. The problem might be that your counterexample actually isn't rigorous. So now we'll look quickly at one way of producing rigorous counterexamples for relation symbols. So I'm going to stick at a slightly more intuitive level. I'm not going to produce a set theoretic account of what the interpretation is, but just tell you how you can produce a set theoretic picture of what interpretation is. So here's how you can do it, is you can just write down nodes for the different elements of your domain. So this, of course, will only work if you have a domain that's finite. But if you have a finite domain, you can write down a dot or a letter, as I've done in this slide here. A and B are elements of my domain. And then put an arrow between two elements of your domain to signify that the relation holds. Again, it's up to you to decide what things you want the relation to hold between. What you do when you write down all those arrows is you've produced a situation, an interpretation of the relation. Okay, so what we'll do first here is let's just look at this example I gave where A bears the relationship to B. B does not bear the relationship to A because there's no arrow going back from B to A, and neither bears the relationship to itself because there's no arrow from A to itself, no arrow from B to itself. So let's just look at these sentences I have below and see, are they true or false in this interpretation? Okay, so exist X, exist Y, Rxy. That says there is an X and there's a Y such that X bears the relationship to Y. That's true because A bears the relationship to B. So there are two things such that A bears the relationship to B. Okay, now let me just point out to you that if I wrote down another interpretation, so suppose I wrote down an interpretation that had just one single element in the domain, A, and just said A bears the relationship to itself. That first sentence is still true in that interpretation because X and Y don't need to be distinct things. So it says exist X, exist Y. They could be the same thing that bears a relationship. X bears a relationship to Y. So that sentence is also true in the interpretation where there's just one thing that bears a relationship to itself. Okay, so now look at the second sentence in the middle there. The sentence in the middle says, any two things, if the first bears a relationship to the second, then the second bears a relationship to the first. So crucially, the order in these relations matters. The first says, if Rxy, then Ryx in the opposite order. So what that says pictorially is if there's an arrow going in the one direction, there must be an arrow coming back. That's not true in the example, the first example there of A arrow B, because there's no arrow coming back from B to A. It is true in the example of just the A with the circle, because there, again, A in itself, again, can play the role of both X and Y. So it is true in the first diagram with A and the loop that for any two things in the picture, if the first bears a relationship to the second, so does the second to the first. Okay, now to the third example, there is something that bears a relationship to itself. That's false in the case where you have A and B and an arrow from A to B because there's nothing that bears a relationship to itself. There's no loop. It's true in the interpretation where there's just one thing that has a loop. Okay, so that's the way these diagrams represent a state of affairs, a situation. Then you can ask whether a sentence with a relation symbol is true or false relative to that interpretation. So let's just do one practice exercise. So now look below to the exercise. this asks me to provide one interpretation in which the sentence is true and one in which it is false. Okay, it may be helpful. I'm going to try first to just think what the picture would look like for the sentence to be true. This says there is something, so well, that's good to start with to make it true because we just need one thing. There is something such that anything that bears the relation to that thing bears the relation to itself. There is something such that anything that bears a relationship to it bears a relationship to itself. So I'm just going to draw a picture now under that, thinking about that. I'm going to draw A, B, now that's an interpretation I just produced. It's a picture I made and a situation I described by drawing the picture. And now I want to show you the following is true. It is true that for anything that bears the relationship to B, that thing bears the relationship to itself, because A is the thing that bears the relationship to B. It's the only thing here that bears the relationship to B, and A bears the relationship to itself. Notice that thing that I just drew, this string of symbols, is actually syntactically ill-formed because B is not actually a name in a name here. It's actually one of the elements of this set, but don't take it more to a slightly more intuitive level. I'm just using that to cash out for you the fact that this sentence, exist X for all Y, RYX, arrow, RYY, is true when you take the A as the instance that makes the exist X true. So A is the thing that makes exist X true. Okay, so that's a case where the sentence is true. Now, of course, that's easy to produce from that a case where the sentence is false, because we can now just write a second diagram where there's A, arrow B. Okay. We're not finished yet because actually, careful. This is going to be an important point. You might think, good, we're finished. There's not a thing such that everything that bears the relationship to it bears the relationship to itself. But actually, that's not true yet. There is a thing in this picture that everything that bears a relationship to it bears a relationship to itself. A, because A, nothing bears the relationship to A. So it is true by negative paradox that anything that bears the relationship to A in this picture on the right, A arrow B, bears the relationship to itself. So A, the following is true, that anything that bears the relationship to A bears the relationship to itself, because this first bit is always going to be false. For any Y, that first bit is false. There is no Y that bears a relationship to A. That's false. We'll make the whole thing, the conditional, true. And so it's true for everything. Okay, so that's not an example yet of making that sentence false. But now notice all I have to do is, if I put a relationship from B to A, now something bears the relationship to A, but A doesn't bear the relationship to itself. So therefore, it falsifies that sentence. Okay, so the second example, we have A and B, and each bears a relationship to the other, but neither bears a relationship to itself. That's actually a counterexample, or a case that makes that sentence false. Okay, so of course there's more information in the textbook, and hopefully you'll get a chance to discuss this in precept. But anyways, this should be enough information to get you going on the last problem set that will ask you to do something just like this.